Okay, we proceed to the next paragraph, paragraph 2.3, about geostrophic flow. And before that, it is interesting to show, okay, it's interesting to show from the previous slide. As we noted before that in the equation 6 and 7 and in 5, that since the Rossby number, which is 2, 6, this Rossby number, and Ekman number, this is 1, are very small in 5. In 5, it's actually the system which we are solving. So this epsilon number, or in fact, Rossby number is about 10 to minus 6 in the Earth, I remind you. This Ekman number, if we take into account molecular value, it's 10 to minus 15. And on my previous lecture, I also told you that while this Ekman number is much less than Rossby number, but nevertheless, we cannot omit that, because actually this value is linked to the boundary condition and with the highest order derivative. So it's small parameter near higher order derivatives. We never it will be neglected maybe in the second instance, but in the first instance we should neglect back the Rossby number. But why not to examine the flow where we neglect by both number? Why not with this system? Of course, we obtain some reduced system, but nevertheless, it's possible to solve it. In some sense, it's the mostly idealized system, and we can get it from this system 2.4, and is with the condition that Rossby number is small, Ekman number is small. So why not to neglect by both of them? So now we proceed to the subject of this lecture. Okay, so after this, I just repeat that since Rossby, and again, in accordance to the formula 6 from the previous chapter, is small, and Ekman number is also very small, and it's a very small number indeed. So are very small in the initial equation 5, which I just showed to you. So the transition from the differential equation from 5 to relatively simple, so-called geostrophic equation, formally obtain it. So it's in some sort of sense of formally we obtain it. We just equate to 0. It's Ekma, epsilon, and E. So consequently, Rossby number and all the terms which connected with it. Of course, this is quite big term which cause a lot of troubles, and it's just simply 0. And also we neglect by viscosity, so we obtain some idealized system. And eventually we have this set of the equations. Let's write it down. So of course we start from the 0, because actually this 0 actually is obtained here after when we neglected by the substantial derivatives. And front of substantial derivatives is this epsilon, which is Rossby number. So we are free to put 0 instead of the substantial derivatives. Then the term which is definitely remain, this is the Coriolis term. It's remain because actually this is the most valuable term in this approximation. Then it multiplied it by the cross product on the z unit vector of z in the axis of rotation, which is directed in the axis of rotation. And of course, we should put minus pressure, more precisely somehow reduce it to normalized pressure, normalize it with density, so there is no density anymore here. But nevertheless, while it's normalized pressure, further I will call it simply pressure, just to avoid some extra wording. So, and of course, the divergence is also equal to 0. Divergence of V is equal to 0. And this is formula 2.8. So this is exactly the formula for the geostrophic flow. And actually, you see that in this condition we have actually we are working perhaps I'll better do it with the mouse. Yeah. Actually, on this condition, we are working in fact, we are working not in spherical coordinate system, but in cylindrical coordinate system, because we have the specially stressed situations that we have some direction which is preferable, and this is direction in the direction of the axis of rotation. This z component is directly in the axis of rotation. So and everything rotates around it. So we have more not. Of course, we can use spherical coordinate as well, but in the sense of the physical nature, it's more easy and more profitable in this geometry to use cylindrical coordinate. And here on this picture, you see that the cylindrical radius is denoted by small s, and spherical and other coordinates are the same as used before. And nevertheless, we can proceed to the general solution of this system. It's a big advantage that this simplified system, which I just showed you, has a general solution. And so the general solution of the system of equation 8, this equation, is most conveniently written in a cylindrical coordinate system. So actually this cylindrical coordinate system is coordinate system in which we have the variable, of course, starting from the z. Then the next is cylindrical radius, s small, and also there is a phi azimuthal component, and it's important to know that this phi is exactly the same phi like in the spherical coordinate. So it's exactly the same phi. So this is somehow united spherical and cylindrical coordinate, that there is one variable which are common for both of them. So, and actually you see here in this picture how it's work. So, and of course we can relate to the spherical coordinate all this stuff by a very simple formula. So this z, we can write like that, is r cosine theta, and this s is consequently r sine theta. And again, I stress that the azimuthal coordinate phi is the same in both systems. Is the same. I just put the explanational mark here. Let us write out for details see the solution of problem of the second problem devoted to this particular chapter. And but at the moment we just directly write all three components of the first vector equation from system 8 in cylindrical coordinate system. Here we have in the vector system, but more convenient to write down this equation in the cylindrical coordinate system because it's quite natural for this geometry, and it's shown on figure 4. So we just write down this system. And of course, we start with 0. And first of all, we consider the component which is in direction of z, of the axis of rotation, the z direction. And of course, this component of this equation, 0 remains 0. And then we have this component which is actually perpendicular to this z. And you know that the cross product of cross vector product of the vectors which are perpendicular to each other is also equals 0. So the only thing which remains here is very simple, and this only thing is minus dp by dz. Let's proceed to another another cylindrical coordinate. And the next cylindrical coordinate, here this especially, it's important to note that here especially the order of how these coordinates are appears is very important. And here we have right-hand order, right-hand screw drive order or something like that. If you take the screw and rotate from Z to the S, if you rotate like that, you see that this screw, you will go in this direction if you have right-hand screw. So this is direction exactly. So we rotate from this to this, and then we get the direction in which this azimuthal coordinate is changed. So we use this rule of right-hand side screw. It's also important to understand how all these things work. And let's now write down the next coordinate. The next coordinate, it's necessary to see, of course, on the cylindrical radius. And I write down just the results, but for you, it is a problem which you show it in more detail, how you reach that. But here I just write down the result. And the special task for you will be to understand how it's working in detail. But here I'm just write down the result. And this 1, 2, a half. It's this half coming from this 2 when we divide it, everything by 1 and 2. And it's dp by ds. And of course, in a similar fashion, we can operate with the azimuthal coordinate, and also in the same sense, as I told you. Of course, this sign which we appear here and here, and here this, of course, very simple. Here the sign appear, especially with taking into consideration this right-hand side screw, and you should be able to show it in the every detail how it works. And it's interesting that if we consider now phi component, you see that there is again sort of the cross. When we consider S component in the component of the in direction of the cylindrical radius, we getting from the Coriolis contribution to the velocity the phi component, azimuthal component, and vice versa if we consider contribution which is coming from cylindrical component, then we have with sign minus, because it's also important, it's working from this screw drive rule. And here we have actual Lamé coefficient, which is going down here. You should be shown this in the detail. And here we have dp by dphi. So there is again some cross on the s coordinate we have a phi, and on the s, while on the phi coordinate we have a c as a contribution of the Coriolis force. So this constitutes the detailed formula which is possible to solve. It's formula 2.9. In every detail for coordinate. Now it is obvious that the azimuthal V phi, azimuthal this one V phi, and radial Vs. Radial I again stress not in spherical radius but in cylindrical radius. Component of the velocity do not depend on the coordinate z. You see that these both components are not depend on coordinate z. This z coordinate which started the most important coordinate which constitute actually the cylindrical system. And are uniquely expressed through the pressure P. So this quite uniquely expressed through the pressure P. To find the vertical component with z, you see that here we have all the velocity vector actually have three components. At the moment, exploring the reduced Navier-Stokes equation, we involved only two components. Of course, there is a third component. How we can get it, this third component? Or maybe first, if we consider in terms of the cylindrical coordinate. So this component, which is directed along the axis of rotation, is what do you think? What we should use to get it? We already used Navier-Stokes equation. Which equation remains? You see? So we should use the divergence equation to obtain this z coordinate of the velocity. So and so we can just expand again in cylindrical coordinate system this divergence vector. So this divergence of the velocity is actually by definition in the cylindrical coordinate system is dependent. It has very simple depending dv by dz. Here, because the coefficient, Lamé coefficient for the first coordinate is 1, so we have this value. Then Lamé coefficient for the cylindrical coordinate derivatives is s, so it's coming this way, and as well it should come to the derivatives s. Consequently, we are in this sense we can put the divergence against the cross vector products. If on the cross vector products and the stress correspondent we have sort of the cross, we take in one value and derivatives from another value, then we will take another value and derivatives from this initially one value, so sort of the cross. Not symmetry, but the cross, sort of the cross. But for the divergence, it's symmetrical function. If we consider the z component, so we are using namely z component of the velocity and z component of the derivative. And the same is working for the cylindrical radius. If we use s component, cylindrical radius component of the velocity, then we use derivatives, partial derivatives in cylindrical components. So in some sense, divergence is sort of the symmetric stuff, not like these cross products. So, and of course we should also add the second component. The last component, the last but not least, of course. Okay, so it's equal 0. So eventually it's constitute equation 2.10. It's interesting to mention that using the coefficient Lamé is somewhat tricky because actually we use this coefficient Lamé here like that, and here we have similar stuff. But when we using the same coefficient of Lamé in the phi direction, then it's just terminate one each other. So only one remains in accordance with the dimension. But here we cannot terminate because it's entered with the same cylindrical value. Here it's going with the same coefficient Lamé, but it's the extra coefficient which appear here just cancelled. So in some sense, this is working like that eventually. So substituting the velocity component expressed through the pressure from 9 into 10, so we have the velocity component, two velocity component, we can express if via the pressure and then put in this equation. So we have Vs, which is represented directly from the pressure, and then we have V phi, which also represented directly from the pressure. So if we put all this stuff there, we put. You can train by yourself, but I am again will write down only the final result. It will be your task to make sure that if we indeed install this and this into this, we are obtaining tremendously simple solution, which is going from this and this, and with some reduced form. So we are obtaining very simple solution, and very important, perhaps the most important stuff in the geophysical flow approximation, that divergency of the z component of velocity, this one, actually we use this one. And also we use this too. Substituting them to this place. And eventually we get simply 0. Very impressive result from my point of view. And but I didn't show the intermediate step. It will be your duty to do that in some task. So it's very simple formula. So in other words, if we notate it mathematically, it's written down like that. But maybe more important in physical sense, because this means that there is no any dependence, of course, in this approximation, of the maybe zero order approximation, or maybe first order, because actually we zero cancel it was. So it means that there is no dependence on the z-axis, at least for the velocity in this direction. Velocity in this direction have no dependence. So it's will take some fixed value in this direction, of course, if we consider it's in this direction. It's an important formula, and it's its own number. 211. Accordingly, the general solution of geostrophic equation 8. So after this step, we can write down the general solution. It's also a big advantage. Equation 8 can be written in the terms of two arbitrary, or in other words, free two-dimensional function p and vz as follows. So we actually, from all this stuff, which we write down here, okay, I just show it like that. From all that stuff, we are getting the general solution. Again, I just will write it down, and it will be your duty to show in every detail how it's works. So it will be sort of the examination. So I just will write down. So we have on the first place, of course, we can have Vz, which is equal Vz, and it's necessary to stress that it's independent of z coordinate, so it's dependent only on s and phi coordinate. So this is sort of the arbitrary function, two-dimensional. It's necessary to stress that it's two-dimensional, because initial problem is three-dimensional, but this arbitrary function is two-dimensional. Then there is another one comes in the play, and another comes in the play. So if we consider, here we consider the z component of the velocity. Let's next consider the phi component. And the phi component from this equation is equal to the derivatives in the cylindrical radius of the pressure. And finally, if we consider the S component, then we have now again in accordance with this Screw-Drave rule, we have that Vs component is equal minus 1/2. Here it's always 1/2 pair dp by dphi. Here you see again sort of the cross. We're getting one component, and the sort of on the cross we have the another component, and the same is here. We're taking one component, and on the cross have another component. And it's important to stress that the second arbitrary function appear, because actually from this equation it follows that pressure is also independent on the z coordinate. It's again it's obvious result. Also, of course, needs some proving, and it will be your duty to prove that, to understand and to show us how it works. So, but here I just will write down the result. And its result is that the P is dependent only on cylindrical radius and phi. So this is, of course, also a rather important formulation, which formulates the general solution and dissolve its own number to 12. This solution. So, okay, let me stress again. What means the general solution? The general solution, 3D solution, of course, this is 3D solution. Actually, this general solution, it means that it depends on some arbitrary function. Because the problem is 3D, so arbitrary function should be 2D. It's the rule of all the general solutions. So that arbitrary contribution to this general solution in order to satisfy boundary condition, in order to satisfy other condition which you impose on that system, on this system. Usually this condition is 1 times lower than initial condition. So I just let me stress that there is arbitrary function which we can choose. At the moment when we consider a general solution, we just put them as arbitrary. But further we will proceed, of course, to some particular case of this general solution, maybe most important case. Then we have, okay, let me trace it from the above to make some difference. So this is one, and this is the second. And depending on only these two arbitrary functions, we can get exact solution for all others. It's just necessary also to stress that there is no dependence on time. So it's, from one point of view, it's even there's some advantage of this system, because we can vary in time all this value, for example, even initial function, and this other function which is expressed in this term will be momentarily follow the rule which on which we can develop this arbitrary function. So as for the simplified, so this general solution 12. This is essentially the Prior-Taylor theorem. There is even the special Prior-Taylor theorem. And this theorem proves that the flow does not depend on coordinate z directed along the axis of rotation when the nonlinear and viscous forces are negligible. There is a theorem, actually. And of course, I show you all intermediate steps how to prove this theorem. But some detailed steps I omitted. So it will be your duty to understand how this very detailed steps are working. And eventually you should prove the Proudman-Taylor theorem, because perhaps this is Proudman-Taylor theorem is maybe one of the most important, if not the most important theorem in geophysics. Because actually it works not only in the Earth's core, it works in atmosphere, it works in the ocean. So it's quite general formula, and the geostrophic flow, which is fast rotating, and when the this Rossby term, v grad u, and derivatives of the time could be neglected. So let me formulate it one more, that just for your understanding. This theorem proves that the flow does not depend on the coordinate z directed along the axis of rotation when the nonlinear inertial and viscous forces, it's necessary to stress that inertial forces are nonlinear, so it's actually linear solution, of course. And viscous force also we remove because it's actually has a very small Ekman number. In some idealized situation, we can do that. And so in our notation, if this theorem is working for the case when Rossby number or epsilon in our case is not, and when the Ekman number, which we denote like E, capital E, is also is not. So actually, why they is not? Because they just compared with the Coriolis force, this one, Coriolis force. And this Coriolis force I show you in the previous slide contains OD1 multiplier, and pressure also the same, and divergence also the same, but all other terms are contain only small contributions, so we can neglect them. Against I just should state that this Coriolis term is the most important, and first of all, it's balanced by the pressure. Okay, and it's linear. So for the simplified system 8, which I showed you before, okay, and here it's also shown for the simplified system 8 and the corresponding general solution 12, this general solution. So simplified boundary condition must be set. You see that the problem is actually very severe problem. If you remember, for the Navier-Stokes for the Navier-Stokes system of the equation involving divergence, of course, zero divergence. For this case, we have to set 6 boundary conditions. Roughly, the amount of the boundary condition could be calculated if we take the highest order derivatives. For example, in Navier text equation, if we have this, then we have the highest order derivative. And this highest order derivative is 2. And there are 3 equations with these higher order derivatives. So we just simply multiply 3 by 2, and we get the number of the necessary boundary condition. But here situation is changed. We neglected by viscosity, so we omit 1 extra order of magnitude, which allow us to involve the extra boundary condition. Here the situation is reversed. We have the highest order in differential term, 1, just 1. And so and again we have 3. So we actually have just we should reduce the number of the boundary condition to satisfy this reducing system. Of course, in some sense it's sort of the downgrade the importance of the solution, but nevertheless, in some general cases, especially when this Ekman number and Rossby number are indeed small, it's work and it's produce some maybe even too simple solution, but nevertheless very important geophysical solution. So the simplified system 8 and the corresponding general solution 12 simplified boundary condition must be set. The number of these boundary conditions must be several times less than the 6 boundary condition represented in 5, due to the fact that the order of system 8 with E equal naught is several times less than for the system of equation from 5. 5 is the full equation, which I show you many times. I hope you remember it. I will not show you again. Physically, the most justified boundary condition for 8 are those that correspond to the obvious fact that the liquid does not penetrate beyond the rigid boundaries. Situation is actually even more severe. Frankly speaking, we don't able to say how exactly many boundary conditions we should impose here. So sometimes we can, in accordance with the real situation. But there seems no doubt, so if we consider, nevertheless, there is almost no doubt that if we consider the velocity flow, it cannot penetrate from the outer boundary. So if we have the outer boundary, so it cannot penetrate from the outer boundary. It's always stop. And so is this corresponding mathematical relation which states that, is that if we consider r component of the velocity, which is directed in spherical radius, it's important to note that the real boundaries are spherical here. So now the play is that we have considered cylindrical system, but the boundary condition is in spherical system. And the first boundary condition, which is the most important, is at the outer core, as far as maybe you remember, that we normalize the size with the radius of the inner core. So the outer core will have the dimensionless radius, which was specified by C. We did that before. And it's, of course, greater than 1. For the Earth situation, this is about 3. So it's about 3 times. And this, if this liquid cannot penetrate from the outer boundary. Of course, it cannot. It's a very simple formulation. We just put 0 here. And of course, it cannot penetrate to the inner core, to the inner boundary. So we are sure that for the inner boundary, we are not. When R is equal 1, it's also not. And this constitutes important formula 2.13. Accordingly, it's if we apply this two-boundary condition, very simple two-boundary condition, then we accordingly the geostrophic flow under consideration in the main volume is determined by 12. With boundary condition 13. This flow consists exclusively of differential rotation not yet defined here. So actually, after this manipulation, it again will be your task. I will just show you the final result, but you should make this manipulation, applying this boundary condition, and to understand how this general solution works with this application. So it will be your home task, if you like, and on the okay, you have very many home tasks. You should proceed from every detail of this calculation in precise way. I omitted some of them, just jump to the result, but your duty will be to show in the every detail how it works. So it will be, so actually we can ask you to show for all of this stuff, or maybe just for particular part of this stuff. So it will be sort of the many problem which can be breaking on the small problem and general problem. So, and you should train yourself just to understand how it works. Hopefully you will do. You will do. Yeah, sorry, you will do. So accordingly, the trophic flow under consideration in the main volume is determined by 12 with boundary condition certain. This flow consists exclusively of differential rotation not yet defined here. So finally, the application of this boundary condition, this two boundary condition, is that Vz is simply not. It's a very interesting result. Then V phi is simply some function of cylindrical radius only. It's important to stress. Some function of cylindrical radius only. And now it's again arbitrary function. Then it's interesting to know that this arbitrary function related with the pressure. 1/2 dp by ds and I should stress that here it's not partial derivative, it's direct derivative, because p is dependent only on s, and this is consequences of the boundary condition. And also there is another simplification that cylindrical coordinate of the velocity is simply not. And as I already told here, that the pressure is just function of cylindrical radius alone. So actually we use two boundary conditions and reduce it to the very simple solution which have only one arbitrary function. Only one arbitrary function. So if we impose the third boundary condition, or another condition, whatever you like, you can impose not boundary condition, but the condition which, for example, for thermal wind, there is different. Thermal wind is very popular in the atmosphere. Of course, in this case, you should add the thermal term as well. But nevertheless, it seems that the here game that we initially has a 6 boundary condition. And so if we reduce it almost 2 times, we reduce it the order of the system. So effectively, we should have 3 boundary conditions. 2 of them I already show you, and 1 remains. So this game plane is in such a sense that if we have arbitrary function, so you have actually could apply 1 more boundary condition just to identify this by applicable this function. And sometimes it's not necessary boundary condition because very often case that near the boundary some viscous layer appear. So you should match not to the very boundary, but you should match to the viscous layer, which is in this case usually Ekman layer, which we will discuss before. And you just apply this condition not exactly to the, you apply this boundary condition, sorry. Okay, anyhow, this boundary condition will work for that to identify this arbitrary function. Of course, there is another way. You can use not necessary boundary condition, but actually you can use some additional condition just to specify the pressure, and we show that. And very important, I get the what I wanted to say. The important thing is that for this extra boundary condition, we should apply not directly to the boundary, but the upper. For example, we have some boundary layer, which lower part, let's just for definition suppose that the lower part of this boundary layer is directly on the boundary, but there is some upper part where the viscous boundary layer is actually disappeared. And we match this geostrophic solution not to the real boundary, but the upper boundary of this viscous layer. This is sort of the trick. And it's also needs some art to understand how it's work. So, okay. Yes, so in some sense, this general part of the solution can be specified as I already told, with consideration of, in fact, these terms which we omitted. So to understand how it, in some general sense, we are going to this step, and we stop here at the moment, and then now we should, there is no way to work in this approximation when the Ekman number and Rossby number are not. To proceed further, even with such a simple solution, we should involve more higher derivatives, which will constitute some viscous layer, which is on the boundary and which is which is on the boundary and which show how it is working. But not only on the boundary. There are some shear layer appear, and the most important one is on the tangent cylinder. And it also has inner part, outer part, and even more situation is even more complicated. There are many different shear layers which are nested in one. So it's sort of a big collection of the different layers. Basically, all of them are fixed, but not all of them with Coriolis force. Ekman layer, for example, with Coriolis force, and the other layer maybe with the other force. And so, but nevertheless, eventually we will obtain the exact solution of this problem, how it's state. Let me just remind that at the moment we considering just differential rotation. And the result, you see that in the bulk of the volume, outside of the shear and boundary layer, we see only pure rotation. You see that the only phi component is working. So it's directly rotate only in the azimuthal component. Yes. And change only with cylindrical radius. So it's working azimuthal component and change only with its cylindrical radius. So this is the sort of differential rotation. Again, I stress that it's in the bulk, it's the main part of the volume of the, in this case, of the spherical shell. Of course, there are very important, even maybe more important than this simplified geophysical approximation, are the various viscous layer. And they are, some of them are very thin, some of them very complicated. And perhaps the most easiest one is the Ekman layer, to which we proceed in the next chapter. But at the moment, it seems we proceed all the chapter of this. Okay, so maybe there is some questions. Maybe somebody. Okay, please.
Can you explain again how you arrived at those boundary conditions?
Which boundary condition?
Vs equals V that equals 0.
Vr equals 0.
Yeah, no, the last leaf. Last line. V that equals 0. Vs equals 0.
Vz equals 0. Yeah. Actually, Vz equals 0. It appears that if we consider the boundary condition, you see that it depends only on f. If you consider in this case the boundary condition that it's not on the inner sphere and it's not on the outer sphere, and it depends only on f, so this situation may be that only may be satisfied only in the case when it's true. Because it's on the, if we consider some vertical axis and then move from the inner core to the outer core, there is two different positions, and both of them, this Z component, which constitutes the air component, is equal to, more precisely the air component, but the main contribution in this geometry is coming from the Z component. So eventually that becomes something for example. Of course, it's possible to explain it in another way, maybe more common. I hope you will do that. Okay, maybe there is one more question, or two, or three. Is there any more questions?
Now it has been reduced to two-dimensional case or one-dimensional? It has been reduced to three-dimensional.
Yeah.
It has been reduced to two-dimensional case.
Yeah, actually it's been reduced to the two-dimensional case with the arbitrary function. One dimension. It is reduced to the two-dimensional case. And this is the rule. If we have the case which is two-dimensional, then the arbitrary function is to apply one dimension work. So arbitrary function is one dimension. Yeah.
At least we are getting ordinary.
Yeah, yeah. And not all dimensions ordinary, linear, so we can very easily get them.
No more questions. Yeah.